Okay, so 2.4, we're looking at the chain rule. Up until this point, we've looked at a number of different rules and when and why we would use them. So quick little reminders, we have our power rule. To use our power rule, we do need to see that our function is some base of x raised to some exponent of n, meaning that if it was in this form, 1 over x to the n, we do have to rewrite that as a negative exponent. If we have a radical, we need to rewrite that as a fractional exponent, right? All resulting in kind of getting it into this form for power rule. We have product rule, which allows us to take the derivative of two functions when they are multiplied. And there's no way around that, right? If you see two functions multiplied, you have to use product rule. The only way to be able to not use product rule is if you can somehow get rid of the multiplication, which is something we've looked at. And that's then when you do your 1d2 plus 2d1. Okay? And then we looked at quotient rule, which was anytime we saw two functions divided. And again, there was no choice in that matter either. If you saw two functions divided, you have to use quotient rule unless you can somehow get rid of the division. Okay? But if you can't get rid of the division or choose not to, you do have to do quotient rule, the low d high minus high d low, all over low squared. Okay? And so that's your quotient rule. You'd work through it, just kind of piece by piece, very intentionally, very slowly, making sure that you're watching for those common errors that we've talked about in class. Okay? Which brings us to the chain rule. So, how and when do we use the chain rule? We use the chain rule anytime we have one function sitting inside of another function, aka a composite function. Okay. And a good clue that you are going to be using the chain rule is you do want to look for parentheses. And it's always nice when those parentheses are already written, but sometimes those parentheses are implied parentheses, and we'll look at some examples of that here in a bit. But anytime you see a function inside of another function, you have to do chain rule. And so chain rule is this. That outside function, the f, you take its derivative. Derivative of f is f prime. And then you leave the guts alone. The g of x stays g of x. Nothing about it changes. It just sits within your outside function, your f function. After you've completed taking the derivative of the f function, then you take the derivative of the g function. Okay? And so that's chain rule. And again, there's no way around it. If you see a composite function, if you see those parentheses indicating a function inside of another function, even if product rule is already at play, you still have to do chain rule when you're taking the derivative of that composite piece. And we're going to look at those as well a little bit later in these examples. But for a bit here, we're going to focus just on chain rule. Okay? Now, before we do some examples of that, I do want to reference a problem that we did recently, or it was one kind of like this. Not exactly like it, but one pretty similar to this. Just to make sure we remember that there are options at your disposal. Okay? So this was in your homework recently. You were asked to take the derivative. We now know that this is potentially chain rule. I see a function inside of another function, but you didn't know chain rule when you were assigned this problem. What did you do when you were assigned this problem? Okay. There are kind of two possible answers depending on which boat you kind of find yourself in. Some people chose to do product rule. So we have our 5 minus x times our 5 minus x. They did their 1 right here, 5 minus x. d2, the derivative of 5 minus x is negative 1, plus 2, my 5 minus x. d1, the derivative of 5 minus x is negative 1. And if we distribute those negative ones, we get negative 5 plus x minus 5 plus x, which is negative 10 plus 2x. And some people went that route when they saw it. Others chose to FOIL that 5 minus x times 5 minus x, giving themselves 25 minus 10x plus x squared. And then because they had gotten rid of the multiplication, they no longer had to do power rule, they no longer had to do product rule. They were allowed to just do power rule, which is to take the derivative of 25 and get 0, the derivative of negative 10x and get negative 10, and the derivative of x squared and get 2x. Okay? And so some people chose that route. We now have chain rule in the mix as well, so technically speaking, if we were to go back in time, now knowing chain rule, we could solve this problem with chain rule, which is to take my outside function, my f, which in this case is this squared, it's the function outside the parentheses, and then we take the derivative of the squared, which is power rule. So we'd bring down that 2 in front, we'd subtract 1 from the exponent, and then initially my g of x, the function inside of the parentheses, inside of the f, it stays the same. And so my g of x in this case is 5 minus x, so it would stay the same. And then we would do the derivative of that function inside of the parentheses, that function inside of my f. And the derivative of 5 minus x is negative 1. And so since we have a 1 exponent, we're allowed to distribute. So if I distributed the 2 and the negative 1, we'd get negative 10 plus 2x, which is the same thing we got using our other two methods. And so you might be sitting there like, well, why would I ever use chain rule? If I can just FOIL it and do power, or for those who are more comfortable with product, if I can just do product, why would I ever need chain rule? Well, imagine for a second if that squared had actually been a 7th. I wouldn't want to FOIL that. I wouldn't want to do product rule on that. And that's where chain rule comes in especially handy, is for a function like this, or one potentially that we can't expand or use any other method on. Okay, and so that's what we're going to explore here with our first several examples, is what are those functions that we definitely want to use chain rule on. Okay, and so here we go. All of our derivatives, or sorry, all of our examples are going to have the directions, find the derivatives. Okay, and the first one we're going to look at is y equals 3x, or the quantity of 3x minus x squared to the 5th. Okay, so you could FOIL this out or do product rule on it. Like I said, I wouldn't want to. We see parentheses. We see a function, 3x minus x squared, sitting inside of another function with that 5th. Those are our cues, or some of our cues that chain rule is at play. So I'm going to go ahead and apply chain rule. We have dy dx equals, so my outside function, my f, is this 5th. And so I'm going to go ahead and bring that 5 down in front, subtract 1 from the exponent, and then remember the guts need to stay the same. G of x stays g of x. So this 3x minus x squared is going to stay 3 minus x squared. It's only after the fact that we then take the derivative of that g of x. The derivative of 3x minus x squared is 3 minus 2x. And so then that would be your answer. You have your 5, your 3 minus 2x, and your quantity to the 4th. Okay? So we're going to do several of these. My recommendation would be, if not on this example 2, excuse me, sorry. If not on this example 2, to maybe on example 3, pause the video, give it a shot on your own. Restart the video either when you're stuck or you have an answer that you're wanting to check. That way you're starting to get a gauge as to what you're understanding, what you aren't understanding, so that when you do come back to class, you have specific questions you are prepared to ask. Like, every time I did an example, I kept getting stuck at this point, or whatever the case may be. Right? But if you want to follow along for one more example, that's fine. Or you could pause now if you'd rather. We have f of x equals the square root of 2x plus 1. Okay, so this one is also chain rule. This is one of those instances where we don't have the parentheses specifically written, but they are there, right? Because if I were to rewrite this function, we have 2x plus 1 to the 1/2, and there are my parentheses. We see a function 2x plus 1 inside of another function, the 1/2. And so you know to take this derivative, you have to apply chain rule on this function where the chain rule exists. Okay, so we're going to do the outside function, that 1/2. Bring that 1/2 down, subtract 1 from the exponent. And then again, the g of x stays g of x. It hasn't changed. G of x stays g of x. And so our 2x plus 1 is still there. Then after the fact, we take the derivative of g. The derivative of 2x plus 1 is 2. Okay, 1/2 times 2 is 1. And so our answer would probably show up as either 2x plus 1 to the negative 1/2, or, because it's a negative exponent, 1 over 2x plus 1 to the 1/2. Or potentially, we do know what a fractional exponent is. An exponent that is a fraction is a root. And so you could potentially see this. Okay, 3 different forms of the same answer. Okay, example 3, we have g of x equals 1 over 3x squared plus 1 quantity cubed. Okay. So again, if you haven't paused the video, I would start considering, if you're going to give it a shot on your own, but here we go. This one, we need to rewrite this function if we're going to use power rule on it. We see parentheses, we see a function inside of another function, so this function down here is chain rule. But if we leave it down here, we also have quotient rule at play, right? And I don't really want to use quotient rule right now, so I'm going to rewrite this as a negative exponent. Okay. Okay, so then applying our power rule here, I'm going to go ahead and bring this negative 3 down in front. Subtract 1 from the exponent, and then my g of x stays g of x. After the fact, take the derivative of g of x. Derivative of 3x squared plus 1 is 6x. And so we've got our answer. Either negative 18x times 3x squared plus 1 to the negative 4th, or negative 18x over 3x squared plus 1 to the 4th. Okay. So example 4 here, we are looking at h of x equals cube root 12x squared minus 6x plus 5. Okay, this is the last one we're going to do in this form. So if you haven't already paused the video, do so now, because after example 4 we're going to throw in a new kind of form for our chain rule. Okay, so this one, rewriting it, we'd have 12x squared minus 6x plus 5 to the 1/3. Which means our derivative, taking that outside function, the 1/3, dropping it down in front, subtracting 1 from the exponent, and then g of x stays g of x, 12x squared minus 6x plus 5. After the fact, times the derivative of the guts. The derivative of 12x squared is 24x. Derivative of negative 6x is negative 6. Okay. So then you have your answer. This 1/3 does simplify with the 24 and the 6, so we would either have 8x minus 2, right, distributing that in, times 12x squared minus 6x plus 5 to the 2/3. I'm sorry, negative 2/3. A little negative there. Or 8x minus 2 over 12x squared minus 6x plus 5 to the 2/3. The other possibility is we do have a 2 in common up top there. They could potentially factor that 2 out. Like so. Okay. Okay, the next kind of style of chain rule are ones that look like one of the following. So we have f of x equals cosine of 5x and y equals secant squared x. Okay. These are both chain rule as well, and there's a couple of reasons we know. One, there are parentheses here that we don't specifically write, but they are located within these functions. You have an additional tool for helping you catch that this is chain rule, which is the derivative rules that we know. In our last set of notes, we wrote down what the derivative of sine x was. We wrote down the derivative of what cosine x was, tangent, sorry, that's supposed to be an x right there, cotangent, secant, and cosecant. Okay. So these are all in your last sets of notes. I want you to take a hard look at the trigs that we know the derivatives of and compare them to the two examples that we have written on our page here, because this is the other clue that you know chain rule is at play. Notice in all of these trigs, my trig has no numbers in it. Right? Singular trigs, as opposed to having two trigs here in example 6. And notice what's the function inside of the trig. Singular x, 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 as opposed to 5x. Okay? The fact that there is any sort of number inside of your trig is the other reason that you know there's chain rule. You know that there are parentheses there. And so then the goal in figuring out kind of how the chain rule plays out is just making sure you know where the parentheses are. And that's where it's going to be really important that you pay attention to where your number is located. In example 5 here, my 5 is with the x, meaning my parentheses are around that x component. In example 6, my number is with the secant, which tells me that my parentheses are around the secant component. And so where that number is located is going to be very communicative for you as to where your parentheses are supposed to be, and it's going to help highlight how the chain rule plays out. Because at this point, chain rule is exactly what we have been practicing, which is the derivative of the outside, leave the guts alone, the g of x stays g of x, and then we multiply by the derivative of those guts. And so in example 5 here, my outside function is the cosine, right? The derivative of cosine. The derivative of cosine is negative sine, but not negative sine x, negative sine 5x. Remember, the g of x has to stay g of x. You can't change it. After that, we take the derivative of our g of x. G of x is 5x in this case, so its derivative would be 5. And that's your answer. In example 6, take a look at what our outside function is here. Outside function is that squared. Like examples 1 through 4, we've got our exponent, so we're going to go ahead and take that exponent, drop it down in front, subtract 1 from the exponent, but make sure your guts stay the same. G of x stays g of x. Nothing changes about it. After the fact, we take the derivative of secant x, which is secant x tangent x. And so that's your answer. Okay, so we're going to do 2 more of these. Again, my recommendation, you've kind of seen 2 of them modeled. I'd recommend pausing the video as soon as we put example 7 up, restarting it when you're ready. That way you're getting a chance to kind of gauge what is it that you are resonating with, what is it that you are understanding, and what is it that you're kind of hiccuping on that you want to make sure you ask about when you come back to class. Okay? So example 7, we are looking at y equals cosecant of 5x cubed. Okay? So this one is chain rule, because there are parentheses, and because there's a number. Remember, none of our trigs have numbers with it. Any trig, any number anywhere in our trig is an indication of some sort of chain rule. And so then the question is, where are the numbers? Are they with the x, like in example 5? Or are they with the trig, like in example 6? Because that tells us where our parentheses go. In this one, they're with my x. This is like example 5. This tells me my parentheses go around the x component. Okay, so then taking the derivative, we have the derivative of the outside. Derivative of cosecant is negative cosecant cotangent, but now it's not negative cosecant x cotangent x. Remember, we have to leave the guts alone. We have to leave that g of x as g of x. So it's negative cosecant 5x cubed cotangent 5x cubed. Okay. Then the derivative of the guts, which is the derivative of 5x cubed, is 15x squared. And that's your answer. Okay, one more specifically in this form. Example 8, we're looking at g of x equals tangent to the 5th x. If you haven't already paused the video, I'd do it now. Okay, so again, I've got a number inside my trig. Tells me that there's chain rule. So you need to pay attention. Where's the number associated? Is it with the x, like examples 5 and 7, or is it with the trig, like example 6? Because then where the parentheses are changes. In example 8 here, my exponent, my number is with the trig, like example 6. And so that tells me that my parentheses go around the trig. Okay, so then my outside function, that 5, I'm going to go ahead and bring down the 5, subtract 1 from the exponent, and then the g of x stays g of x. Those guts don't change. Then we take the derivative of the guts. The derivative of tangent is secant squared. And we've got our answer. Okay, so we're going to keep looking at some some chain rule here, and definitely some trigs in the mix. But we do need to start looking also at some product and quotient thrown into the mix. And so we're going to start to expand our view of this rule here with example 9. Okay? Starting with example 9, we're going to do 3 of this type of problem. So like I've said before, I'd maybe watch the first one, maybe first 2, but the first 1, and then I would start pausing the video to give myself that independent time practicing at home. Make sure you are owning that practice time, right? So example 5, we are looking at f of x equals x cubed cotangent of 3x. Okay? So looking at this, it's always good with your derivatives to really slow down, to pause, to think, and to ask yourself, what rules do I see at play? You want to make sure you don't jump too quickly into it and so then leave out a rule that you have to use, that there's no way you can get around it. Remember, we started this video note out with reviewing those rules. And so as you look at this rule, what are some rules you see at play? And hopefully we're identifying that there's product rule here, because we see we have two things being multiplied together. There's no way to not use product rule unless you can get rid of the multiplication. Unfortunately, there's no way to do that with this particular problem. So we're going to be using product rule. There's also power rule with your x cubed. You've got your trig rules with that cotangent. And then our newest rule is our chain rule. Notice that we have a number with our trig. We have cotangent 3x. So this is like the examples 5 through 8 that we just did. We have to therefore do chain rule if we take the derivative of this function here. There's no way around it. You can't just not use chain rule because you don't feel like it. If you are taking the derivative of cotangent 3x, you have to do chain. Okay? And so let's go ahead and walk through this. I am going to rewrite this function with my parentheses. Where are my parentheses in this one? And hopefully you thought around the 3x because the 3 is with the x. This is like examples 5 and 7. Pay attention to where the number is. It helps you kind of get your parentheses in the right spot. And so then we've got our product rule to kind of start us off with chain rule thrown into the mix along with power and trig. Okay, so product rule. 1, my x cubed. D2, derivative of my second. Well, remember, this is chain rule. So right now, as I'm doing the D2 of my product rule, I have to do chain rule in that spot. It's how I take the derivative of this second function where chain rule is located. Okay, so we're doing D2, derivative of the outside is negative cosecant squared. Leave the g of x alone times the derivative of g of x. That's my D2 here. 1 D2 using chain rule. Plus my 2 cotangent of 3x. D1, power rule. Derivative of x cubed is 3x squared. The rest of power rule. 1 D2 plus 2 D1. And so then that is theoretically your answer. We have our negative 3x cubed cosecant squared 3x plus 3x squared cotangent 3x. So theoretically the answer. Now there is one more thing that could be done on this problem though. What if you were taking a multiple choice test and that didn't show up as an answer? What else might they have done looking at what you've got on the page there? Okay, and hopefully we recognize there's a like term that could be factored out here. You could either factor out a positive 3x squared or a negative 3x squared. I'm going to go ahead and factor a negative 3x squared out. And so left over in here, if we pulled out a negative 3x squared, we'd have x cosecant squared 3x. And back here, pulling out a negative 3x squared, we'd have minus cotangent 3x. And so it's possible this would also be an answer. Okay. Okay, example 10. Again, we're doing 3 of this style, so at some point make sure you're pausing the video and trying it on your own. Okay, x squared times the quantity of x cubed minus 1 to the 4th. Okay, so what rules do you see? We see multiplication, so you have to do product rule, no way around it. Well, okay, actually, no, that's not true. There is a way around the product rule, but to get around the product rule, you'd have to FOIL out this x cubed minus 1 to the 4th, so expand that 4 times, and then distribute the x squared in, which is kind of a waste of time. But technically speaking, you could. Okay, but there's product rule, two things multiplied together. We've got chain rule. We see some parentheses, a function inside of another function. So when if I want to take the derivative of this term, I have to do chain rule on it. We've got product rule, we've got the constant rule, we've got the difference rule. I'm sorry, power rule. Power rule, constant rule, and difference rule as well. Okay, and so here we go, product rule. Like two functions. Okay, we have our 1 x squared, d2, okay, derivative of the second function where chain rule is located, so we have to do chain rule. Let's bring down that 4 in front, subtract 1 from the exponent, and make sure that that g of x stays g of x before taking the derivative of g of x. That's my d2. Derivative of a composite function has to be chain rule. Plus my 2, x cubed minus 1 to the 4th, d1, derivative of x squared, is 2x. Okay, so cleaning that up, we have 4 times 3 is 12, x squared times x squared is x to the 4th, and at the back here, just kind of putting that 2x in front. And it's possible that might be your right answer, but what if it was a multiple choice test and you were looking at your answer choices and you didn't see that as your answer? What else might they have done? Okay, we have some like terms in common. There's a 2x that could get pulled out, and what? X cubed minus 1. How many x cubed minus 1s? 3. There are 3 that they have in common. So I could pull out a 2x and those 3 x cubed minus 1s. And so then you'd be asking yourself, well, what's left over after I pull that 2x and those 3 x cubed minus 1s? In my first term, pulling out a 2, I'd have a 6. In an x, I'd have an x cubed. All 3 of these x cubed minus 1s got pulled out. In the back, the 2 got pulled out, the x got pulled out, 3 of the x cubed minus 1s got pulled out, and so that leaves me with x cubed minus 1. That probably wouldn't show up as an answer though, because there's a positive 1 that you distribute here, right, which would allow us to drop the parentheses. We'd have 6x cubed plus x cubed minus 1, which would allow me to combine like terms. 2x times the quantity of x minus 1 cubed times 7x cubed minus 1. That could potentially show up as an answer. I mean, I guess technically speaking, these could as well. That just would surprise me. Okay. Okay, one more in this form, example 11. We are doing g of x equals 5x to the 4th secant cubed x. If you haven't already paused the video, I highly recommend that you pause the video, give this one a shot on your own. Okay, so what rules do we see? We see product rule, 1d2 plus 2d1. We see power rule. We see trig rules, and right here we see chain rule because there's a number inside my trig. Then where the number is located tells you where your parentheses go. My number here is located next to the secant. And so my parentheses go around the secant. This is like example 6 and example 8. Okay. So when it comes time to take the derivative of that second term, we have to do chain rule on it. No ifs, ands, or buts about it. Okay, so product rule, 1, 5x to the 4th. D2, bring down that 3, subtract 1 from the exponent, leave the g of x as g of x. Okay, then times the derivative of the guts, which is secant x tangent x. Okay, 1 d2 plus 2, my secant cubed x, my 2 here, d1, derivative 5x to the 4th, is 20x cubed. So cleaning this up, 5 times 3 is 15, x to the 4th. We have 2x, or 2 secant x's and a third secant x, and that tangent x, and back here 20x cubed times my 3 secant x's. And maybe that's our answer, but what if it wasn't? What else might have happened? They might have factored. We have here a 5 in common, an x cubed in common, and 3 secant x's in common. So I could pull all of those out. Pull out a 5 and x cubed and my 3 secant x's, which would leave me with what? In my first term, a 3 and an x and a tangent x. And in the back term, a 4, and then the x cubed went out and the secant cubed went out. So that is my potential second answer, potential final answer. Okay? Moving on to our last one here. We're going to again do 3 of these. I recommend watching one, pausing the video on the next 2 to give them a shot. Okay. Example 2, we have 5x squared, f of x equals 5x squared over cosine cubed of x. Example 12. Okay, so what rules do you see at play? Okay, we've got quotient rule, no way around it. If you have 2 things divided, you have to use quotient rule unless you can get rid of the division. We've got power rule. With that 5x squared, we have our trig rules with the cosine. And then we see our new one, chain rule. Chain rule is down in that denominator function, that cosine cubed x. This is like examples 6, 8, and 11, where because that cubed is next to the cosine, my parentheses go around the cosine. Okay. So then here we go. Let's walk through this. Quotient rule. Low, my cosine cubed x. D high, derivative of 5x squared is 10x. Minus high, 5x squared. D low, to take the derivative of this function, because there's chain rule there, you have to use chain rule. So let's bring down the 3, subtract 1 from the exponent, leave the g of x alone, then times the derivative of g of x, which the derivative of cosine is negative sine. All over low squared. Okay. So then cleaning this up, we have our 10x cosine cubed x. Negative times a negative is a positive. 5 times 3 is 15. My x squared, my 2 cosines, and my sine. And it's always nice when you're taking a multiple choice test and you look at your answer choices and that one's there. But what if it wasn't? Okay, in my numerator here, I see I have something in common. There's a 5 in common, an x in common, and 2 cosines in common. So I could pull out a 5, an x, and 2 cosines. What would you be left with? Okay, well, what if I pulled the 5 out? I'd have a 2, the x went away, and 2 of the cosines went away, leaving me with 1 cosine. In the second term, the 5 came out, leaving me with 3. 1 of the x's went away, leaving me with x. The 2 cosines are gone, but I still have that sine. it's potentially possible that that would be the answer, but honestly my guess is that if it were to have been factored, it most likely would also be simplified. Because in this case, we have 2 cosines on top and 6 on bottom. And so I can cancel out 2 of those cosines. So my guess is if it was factored, it would be simplified, leaving me with this as my final answer. 5x times the quantity of 2 times cosine x plus 3x times sine x, all over cosine to the 4th of x. Okay. Example 13. We have h of x equals x to the 4th over the quantity of x minus 1 cubed. Okay. Again, we're only going to do a couple more, so I'd recommend sometime soon pausing the video, giving this one a shot. Okay, quotient rule. We have low x minus 1 quantity cubed, d high 4x cubed, minus high x to the 4th, d low. I've got chain rule down here, so to take the derivative, I have to use chain rule. So let's bring down the 3, subtract 1 from the exponent, g of x stays g of x, and then times the derivative of the x minus 1, which is 1, all over low squared. Okay, and so then cleaning that up, 4x cubed, I'm going to go ahead and bring that to the front of this first term. At the back we have 3x to the 4th, 3 times 1 is 3, and then our x minus 1 squared. It's possible that would be my answer, but what if it wasn't? Okay, they might have factored. There's an x cubed in common and 2x minus 1s. What are we left with? We're left with a 4 and 1 remaining x minus 1. Back here we're left with a 3 and an x. Like the last one, I'm guessing that if this function was factored, it would most likely also be simplified. So these 2x minus 1s on top would most likely cancel with 2 of the 6 that we have on bottom. But there's another thing here with this particular function. Take a hard look at what's inside our brackets over here. What else might have happened there? Okay. They might have distributed 4x minus 4, which would allow me to combine like terms. 4x minus 3x is 1x, and so chances are is that if they factored, they'd probably simplify, they'd probably distribute to combine like terms, leaving me with the x cubed, 4x minus 3x is x, minus 4, all over the quantity of x minus 1 to the 4th. Okay, one more. Example 14. Okay. We have g of x equals x squared over root x minus 1. Okay, so again, pause the video if you haven't already. Here we go. This could be rewritten as x squared times x minus 1 to the 1/2. So quotient rule, we have our low, that root x minus 1, d high, derivative of x squared is 2x, minus high, which is x squared, D low, dropping that 1/2, subtracting 1 from the exponent, leaving the g of x as g of x, and then times the derivative of g of x. All over low squared. And so then cleaning this one up, we'd have our 2x times our root x minus 1. Back here we'd have the x squared times the 1 would be x squared. This 1/2 would give me a 2 in the denominator, right? 1/2. Negative would also send this one down to the denominator, that x minus 1. And then this is a simplification step we've practiced a number of times in class, but we're going to continue to practice, which is how do we get rid of the extra denominator? So extra denominator question mark. Multiply. Okay, so we're going to be multiplying by that 2 root x minus 1. But then doing it to all of them, right? The 2 root x minus 1 and 2 root x minus 1. That will call this extra denominator, or cause this extra denominator to cancel. Okay, so in my first term, 2 times 2 is 4. We've got our x, and then root x minus 1 times root x minus 1 is just x minus 1. Back here we have our minus x squared, and then in the denominator, we have 2, and then we have like terms here, or like bases, I should say. Right? We have x minus 1 to the 1 and x minus 1 to the 1/2. Anytime you multiply like bases, what do you do to their exponents? You add them. So x minus 1 to the 1 and x minus 1 to the 1/2, if I added 1 plus 1/2, I'd get 1/2 or 3/2. Okay, this allows me to distribute my 4x. So 4x squared. 4x squared minus 4x. Which would allow the 4x squared minus x squared to become 3x squared. Which could potentially be your answer. But what if it wasn't? There's an x in common up there, up in the numerator, so we could factor that out, leaving me with this as my final answer. Okay? Okay, that's all.